The next type of differential equations we're going to be looking at involve using a substitution. So when we have differential equations that are of the form m dx plus n dy equals 0, very similar to the exact equations. The difference here is that the coefficients m and n will be of the same degree. So as an example, we're looking at this differential equation here. X minus y is the coefficient m and x is the coefficient n. So if we just look at m and n, which is x minus 1, x respectively, the degree of m is the first degree. You can clearly see that the highest power of the variables x and y is 1, and the highest power of x and n is also 1. So the degree is the first degree for both. So m and n, or the coefficients m and n, are of the same degree, in which case we're going to use a substitution. In this particular differential equation, the substitution we're going to use is y equals ux. You can be any variable you want here. We're just calling 2, could be v, could be anything else, except 1x. Just note that u is not a constant term here. Okay, is it a function of x? So when we take the derivative dy dx, we can use the product rule. So if we hold u constant, we will differentiate with respect to x. The derivative of x will just be 1, so we'll just have u. Now we're going to hold x constant with respect to u, so we'll have plus x, and we're differentiating u, so it'll be du dx. And just cleaning this up and putting to a more readable form, we'll have dy equals u dx plus x du. And what we do now is we're going to substitute in to this differential equation the expression for y and the expression for dy. So we'll have x minus ux dx plus x times dy, which is this expression here, u dx plus x du. And that equals 0. I'm just going to multiply these brackets out, collect all the common terms, group at least all the similar terms together, and then we're going to use variable separable. So we'll have x dx minus ux dx plus ux dx plus x squared du equals 0. So these terms here will cancel, which is nice. So we'll have x dx plus x squared du equals 0. Let's divide through by x here. Obviously, x cannot be equal to 0, so we'll have dx plus x du equals 0. X du equals minus 1 over x dx. Now integrate both sides. So we will have u equals minus the integral of 1 over x dx, u equals minus then x plus the constant of integration. Remember that y equals ux was a substitution we used, so u equals y over x. So y over x equals minus ln x plus c, and the solution is y equals minus x ln x plus cx. Okay, this example is also in the form m dx plus n dy equals 0. Again, notice the degree. So y squared plus yx is m, and minus x squared is n. Notice that the degree of either of these expressions is the second degree. So we have the situation where we're going to use the substitution y equals ux, and then dy equals u dx plus x du. So we're going to sub both of these expressions into the differential equation. So y squared would be ux squared. Yx will be x times ux, and that is dx minus x squared times dy, which is u dx plus x du, and that equals 0. So we have u squared x squared. I'm just going to bring this dx in, dx plus u x squared dx minus u x squared dx minus x cubed du equals 0. These two terms here will cancel, and we're left with u squared x squared dx equals x cubed du. We're just going to take that over to the right because we're going to have variables separable here. So we'll keep the x's on the one side and u's on the other side. So on the left, we'll have x squared divided by x cubed. So we'll have 1 over x dx on the left. And then we divide both sides by u squared. We'll have 1 over u squared du. And then we're going to integrate these two expressions. So we now have ln x equals, let's just write this as the integral of u to the minus 2 du. And then we integrate that, we'll have u to the minus 2 plus 1, so u to the minus 1, and then we divide by the exponent negative 1 plus the constant of integration. So just coming up here, we have ln x equals minus 1 over u plus c. So we'll just take that minus 1 over u to the left. We'll have 1 over u equals minus ln x plus c. We've just flipped that over. U equals 1 over minus ln x plus c. Again, the substitution we used was y equals ux, so u is y over x. So y over x equals minus 1 over ln x plus c. Y equals minus x over ln x plus c. Looking at this expression over here, just to clarify what I did over here, we took a minus sign out from the denominator, so we would have had 1 over minus ln x minus c, and then that minus is then just written in the numerator, so minus 1 over ln x minus c. But because c is an arbitrary constant, we generally write a positive sign in front of the arbitrary constant. It doesn't matter what this constant is. So that's why this minus sign here was written as a plus sign. It's insignificant as far as the solution to the differential equation is concerned, because c is an arbitrary constant. So that's why a plus sign was written in front of the arbitrary constant instead of the minus sign. We can write the solution in a slightly better form. So we'll just multiply both sides by ln x plus c. So we'll have y times ln x plus c, that equals minus x. So multiplying this out, we'll have y ln x plus cy equals minus x. And just take the x over to the left. So we'll have x plus y ln x plus cy equals 0. And we can leave it in this form. It's quite acceptable. We won't be able to, if we do separate the y's, we're just going to come back to this expression in any case. This is just a nice, neater form, alternative form of the solution. The final solution over here x plus y ln x plus cy equals 0 can be written in the form x plus y ln x equals minus cy, just taking that term across there. But again, this minus sign here for the arbitrary constant, it doesn't really matter, right? Because c is an arbitrary constant. So hence it's just a convention that we just remove that minus sign. So we just write it as a positive cy. This differential equation is slightly different because we have a slightly more complex term in x plus y plus 1 all squared. So the substitution won't be the same as it was before. In this case, we're going to let u be the contents of that bracket, which is x plus y plus 1. And then we're going to find the derivative du dx, which will be 1 plus dy dx, and then plus 0. Note that we have an expression dy dx here, so we're just going to rearrange this equation. Dy dx therefore equals du dx minus 1. And then we can sub this expression dy dx and u into the differential equation. So we'll now have du dx minus 1 equals u squared. Du dx equals 1 plus u squared. And we can just rearrange this. So we'll have 1 over 1 plus u squared du equals dx. And then we integrate both sides. So the integral of 1 over 1 plus u squared equals arctan u, or if you prefer, tan to the minus 1 of u, and that equals the integral of 1 dx, which would just be x. Okay, since we're solving for u, that means that u equals tan x plus c. U is x plus y plus 1, so x plus y plus 1 equals tan x plus c, and therefore y equals minus x minus 1 plus tan x plus c, and that is the solution to the differential equation. So with this differential equation, we can see the degree of x in this expression x squared plus y squared. So again, you can call that m if you like, and x squared minus xyn. So in m, the degree of the expression is a second degree, both in x and in y, and the degree of the expression n is the second degree as well. Note we have the product here of x and y, and the degree of each of those expressions is 1. So it's essentially a second degree expression, if you like. Okay, so this will be a differential equation where we're going to use a substitution. So we're going to use y equals ux, and then dy equals u dx plus x du, and then substitute these into the differential equation. So okay, so we have x squared plus y squared will be u squared x squared dx plus x squared minus x times y will be x times ux, so we'll have ux squared. And instead of dy, we're going to put this expression in, so it'll be times u dx plus x du equals 0. It's going to multiply this all out. X squared dx plus u squared x squared dx plus u x squared dx plus x cubed du minus u squared x squared dx minus ux cubed du, and that equals 0. So we have this term cancelling with that term there. And then we can bring the dx's together and the du's together. So we'll have x squared times 1 plus u times dx. So that'll be that term grouped with, factorized with that term, plus x cubed 1 minus u du equals 0. Now we just need to separate these variables. So we're going to divide through by x cubed first. So x squared divided by x cubed will be 1 over x. Then we'll have dx. At the same time, we're going to divide every term by 1 plus u. So we will now have 1 minus u over 1 plus u du equals 0. And then we can put this into variable separable form. Before integrating this expression here, 1 minus u, 1 plus u, we want to put that into a bit of a more of a friendly form. So this expression 1 minus u over 1 plus u, after some manipulation, equals minus 1 plus 2 over 1 plus u. So we have 1 over x dx plus minus 1 plus 2 over 1 plus u du equals 0. And we can now integrate each of these expressions. So the integral of 1 over x dx will just be ln x. We're going to split this up into separate integrals. We don't have to. This might be easier. So we have the integral of minus 1 du plus the integral of 2 over 1 plus u du, and the integral of 0 is just going to be a constant. So we have ln x minus u plus 2, and we'll take the 2 out of the integral, and we have 1 over 1 plus u, which when we integrate with respect to u will just be ln 1 plus u, and that equals c. So we'll now just clean this up and simplify in terms of u first before we go back and resubstitute. So we'll have u minus ln x plus c on the right. We'll bring those two up to the top here by log laws. So we'll have ln 1 plus u squared equals u minus ln x plus c. And now we can drop the natural log. So we'll have 1 plus u squared equals e to the u minus ln x plus c. So we have 1 plus u squared. I'm just going to try and clean this up here. So we'll have e to the u times e to the minus ln x times e to the c. Okay, we'll leave e to the u alone as it is. E to the c, this term here, is really just another constant. So we'll just call that a, and call it whatever constant you like. And then the second term here, e to the minus ln x, we're just going to write, this is e to the ln x to the minus 1. And e to the ln x to the minus 1 will just be x to the minus 1. So that will be, we'll write it as x to the minus 1 for now. So 1 plus u squared equals a e to the u times 1 over x. And now that we've cleaned this up, we can just substitute what we had for u. So u is y over x, so we'll have 1 plus y over x squared equals a times 1 over x e to the y over x. Okay, we can just clean this up a bit. So the left-hand side will be x plus y over x all squared equals a times 1 over x e to the y over x. We have x plus y all squared over x squared equals a times 1 over x e to the y over x plus y all squared equals, you multiply both sides by x squared, and then this x here will cancel with one of them there, so it'll be a x e to the y over x, and we can leave the solution in that form.